Okay, hi, everybody. Thank you for, coming here at the bitter end for my talk, and thank you to all of the organizers for responding to my emails and scheduling me incredibly late. I will be discussing some work in progress with Valentine Kabanets, Antonina, Kolokolova, hi Antonina, and Igor, Oliveira. So what we would like to ask is how difficult to prove lower bounds, circuit lower bounds that we already know. Okay? And the topic of this work is basically, does VPV, which is a theory of bounded arithmetic that corresponds to polynomial time, so efficient reasoning. You can think of it as T02 as defined in Igor's talk yesterday. It has some numbers, it has some strings, it has symbols for all polynomial time functions. For today, there's a cosmetic difference. I just have both numbers and strings in the language, but you don't need to worry about the specifics of this theory too much, just that it represents polynomial time reasoning, and it can prove stuff like Cook-Levin theorem and PCP theorem. So it's a pretty decent theory that can prove some good theorems in complexity theory, okay? So we ask, does VPV prove the circuit size hierarchy theorem? Henceforth, CSH, okay? And this is very straightforward. It just says if you have a bigger circuit, you can compute more Boolean functions, and the proof is by counting Boolean functions and then encoding Boolean functions as circuits and showing that there's more bigger circuits than smaller circuits, okay? So, yeah, so main result or claim, depending upon how in progress this work is, if VPV proves circuit size hierarchy, I will remove these quotes later in the talk, then this implies that P is not contained in slightly superlinear size circuits. So see, I'm intersecting over all epsilon greater than 0. So this, if this statement were true, it would be a kind of an extreme version of Kolmogorov's conjecture, right? Every language in P, no matter if it's like n to the 100, would have like a n to the 1 plus a half circuit. You could drive that size of that circuit down as much as you wanted. This seems extreme, but we don't know how to prove, we certainly don't know how to prove this right now. The best lower bounds we have for general circuits are linear by these very intricate and increasingly sophisticated gate elimination arguments. I think they get up to around the region of like 3.5 n these days. Does anybody know?
It's lower than that.
Oh, it's lower than that. Okay. The best we can do here for general circuits is lower than 3.5 n. Thank you, Paul. In a better version of this talk, I would give an exact citation for the current champion. But the point is, this would be a minor breakthrough in circuit complexity lower bounds. This is a question about feasible proofs of theorems that we already know. So you can either be an optimist and you can say, okay, either all you have to do to prove this circuit lower bound is formalize this proof we already know in VPV, or you can say, well, because this is super hard, maybe VPV doesn't formalize this, or it have to be super difficult to put the proof together. Okay? Okay. Let me tell you the plan before I start not defining VPV. Okay. So here's our plan. The argument will just be by witnessing. Step one. We assume appropriately formalized that VPV proves CSH, and we assume towards contradiction that P actually does have these like super tiny circuits if we want. Two, we witness the proof. What does that mean? So what this says, right, is there's big circuits that don't have languages computed by small circuits. If we witness the VPV proof of this, we get a student teacher printer for the hard circuits. Cover up student teacher for now, ignore it. What would be really nice is we have a Turing machine, I give you n in unary, and then the Turing machine prints out a hard circuit on n bits that no quadratic size circuit agrees with this circuit. That would be amazing. If we could witness this and get that very easily, we cannot. We witness this and we get something slightly more complicated. We have an efficient interactive game where a student says, oh, is this circuit the hard circuit? And then the teacher either says, no, you screwed up. Here's a smaller circuit than your circuit that computes this function, or no, you did it, you're done. And this iterates until they do get to a final circuit that's actually hard in a constant number of rounds. I'll elaborate on this later. Okay, so the point is we can witness this, we get a printer for hard circuits. An efficient printer. Now we're in trouble, right? Because we assume this extreme circuit upper bound. We use that circuit upper bound as the teacher in this game, right? So if there's a polynomial-time algorithm to extract from this proof a printer for the hard circuits, there's also a polynomial-time algorithm to sort of evaluate those circuits. So if we have super strong circuit upper bounds for P, well, maybe these hard circuits aren't so hard, right? We go through this proof to get way smaller circuits than they should be. Finally, we contradict. So this will imply H from CSH. This is the CSH in quotes that we assumed had a proof in VPV, has small circuits. And then this contradicts soundness of VPV. Because VPV is a sound theorem, it should only prove true theorems, but it proved this like jacked up version of the circuit size hierarchy theorem that we're going to explicitly show is false. Okay, so that's the plan. Are there?
Can you repeat step 3?
So in step 3, from our witnessing, we get kind of an interactive, efficient game that prints out hard circuits. We apply the circuit upper bound assumption as the teacher in that game. That gets us, like this theorem says, there's big circuits that their functions, there can't be computed by small circuits. This is where the contradiction will come from. We'll extract 2 small circuits for the functions identified by the circuit size hierarchy theorem. This will become much clearer as I start actually not defining things.
But I should think of this game as being somehow on uniform. I can plug in like an Oracle teacher somehow, and you're free to in particular plug in that.
Yes. I am free to, the teacher is very unconstrained. The student is polynomial time and a constant number of rounds.
Uh-huh.
So that's why I can use this non-uniformity as the teacher. Thank you. That's a, yeah. But this will become clear when we see the actual theorem. So let me not define VPV. It's like T02 from Igor's talk, P time function symbols. The only thing that you need to know for today is that lowercase is number variables and uppercase is strings. And I have symbols for every function in P time in my language. Okay. So let me actually state the circuit size hierarchy theorem. For every k size n to the k, size n to the 7k is not contained in size n to the k. This is a very weak version of the circuit size hierarchy theorem. Of course, you can do much better, but this only makes our setup more interesting because we say, okay, if you can prove this super weak circuit size hierarchy theorem in VPV, something is like okay. Let's formalize this. So circuit size hierarchy of n naught nk. I'm going to define this as the following sentence. So for every n such that n is at least n naught this parameter, there exists an h. H is a circuit on n bits with at most n to the 7k gates, such that for all, I'm just unrolling this, such that for all C, C's are circuits on n bits with just n to the k gates. There exists an x in 0, 1 to the n, such that the following happens. A hard circuit on x disagrees with every small circuit on some x. So all it says is this is like an almost everywhere circuit size hierarchy theorem with a big like polynomial-ish gap between the two circuits. Between the two classes. Are there any questions whatsoever about like this? If this doesn't make sense, we are doomed. Great. So here's a fun claim. Circuit size hierarchy as parameterized here. This is a legit sentence in the language of VPV, right? Like I can actually straightforwardly phrase this. Why is that? Because VPV has, all the p-time function symbols, so I can just evaluate and check these functions, right? I can encode circuits in a reasonable way and make sure that these quantified strings have the right length and the right format to be circuits. And then over here, all I need to do is like use the function symbol circuit evaluation problem to check and compare them. So legit sentence of language of VPV. One thing that I do kind of want to draw your attention to is k is a parameter because I don't want to talk about anything in the exponent that's a variable that screws up my growth rate. This is bounded arithmetic. Okay.
So VPV has smash function.
No, VPV doesn't have smash function. VPV is Cook and Gwen's two-sorted theory, where instead of smash function, they have like these explicit strings and you can take the length of a string, but it has the effects of smash function.
Objects are represented by second-order variables,
Yes.
or first-order variables are indices.
Yes, first-order variables are indices. Thank you. Yeah, so I'm always gonna write lowercase for numbers or indices.
essentially RSUV.
Thank you. Okay. So we wrote down the thing, we said it's a legitimate sentence of the theory, and now we're gonna write our theorem or claim somewhat more precisely. If for each K there is an N naught such that VP proves circuit size hierarchy and not K. This implies the mildly superlinear circuit lower bounds over there. So circuit lower bounds just abbreviates the circuit upper bound negated statement over there. Okay. How much time do I have left? Almost none.
No, about 12 minutes.
Oh, wow, okay. Let's go. So let's take the KPT theorem. This says, this is Krajek, Pudlov, Takeuchi, and the version that I'm using is from this book of Cook and Gwen, where they use the two sorted theories. That was just easier for me to read. It would also work fine for T02 yesterday. If VPV proves a sentence of the following form, for all n, there exists W, again, number, string, there exists W, step for all y, there exists an x, phi, n, W, y, x, where phi is quantifier free. Then VPV also proves a simpler sentence. So what's the whole issue here? Like, what would we want to do? In circuit size hierarchy, see the existential quantifier on H, the hard circuit? That's the existential quantifier on this W over here. Sort of the witness of this formula that, you know, something good is going to happen at every input length for us, i.e. having a hard circuit. So if VPV proves this, then VPV also proves for all n, then we universally quantify over a bunch of Z variables, Z1, Z2, all the way up to Z, we call it R plus 1 for some constant R that is handed to me by the application of the KPT theorem. I don't control R, that will be important. Okay, then inside this quantifier prefix, what I have is I have R disjuncts. Those disjuncts look like this. There exists X such that phi naught N F0 and Z1 X. This is just the first disjunct. There's many more. Let's unpack this. Phi 0 is just phi with this are function symbols. Okay, so what's happening to phi 0? Phi 0 is phi with a function symbol where the witness would go, right? Otherwise, it has Z1 takes the place of Y, but that's essentially the same, right? Because see, Y over here is universally quantified, all of the Z's are universally quantified, and the X is effectively the same, right? So phi 0 is exactly just phi with this particular function symbol f sub 0 substituted in, okay? And what does f sub 0 take in this first phi 0? Nothing, just the index, the input length that we are interested in producing a witness for. We continue with a disjunction. We get a second one. There exists X, phi1, n, f1, and z1, z2, x. Okay, what's going on here? Let's pretend we're doing some kind of interactive game, right? We're looking for a W that fits this sentence. The first clause represents a polynomial-time student's first attempt to print a witness, right? They have no response from the teacher. This is just a polynomial-time function that takes n as input. One of two things is gonna happen at this first clause. Either the student just knows the answer in the first round and this is satisfied. What does that mean? Since Z is universally quantified, this is a good witness. We can stop. We're all set. On the other hand, perhaps the first answer is not the best answer and they need some correction from the teacher. Then it will not be the case that this is true for all Z1s, right? In our circuit setting, this is like, oh, there's a circuit that's too small for you. So we come to the second disjunction. This is like the teacher saying to the student, here's what's screwed up. Here's what you don't have. Yeah?
You mean Fi are definable function symbols, not abstract variables?
Yes, they are definable function symbols of LPV. Thank you.
Include all the functions, VPV.
Yes, VPV has all of the function symbols,
functions.
all of the function symbols just as like little flat
got it,
guys. So
got it,
that's
got
why
it.
this is simple for me to think
Got it.
about comparatively speaking, because I like to have all the function symbols hanging around.
And this also makes it universal, so you can hit it this.
Yeah. So the point is,
There is just one phi,
there's just one phi?
phi 0, phi 1, and so on should be just phi.
Oh, I'm sorry, yes, this. I keep doing this because I number the clauses, because what we're gonna do is we're gonna refute them one by one to get at our contradiction, but thank you, Emil. This is the same exact formula, it's just phi with a different function symbol plugged in at each round. I'm sorry, that was needlessly complicated, thank you. But the point is, there are N, F, R, N, Z1, all the way up to ZR, and we get our final ZR plus 1 over here. We get an X and we close the parentheses. Why is this special and exciting? This is like a very effective Herbrandization of VPV.
But it's partial, you don't care about it. It's partial because you don't put current function on X.
Yeah, it's partial. I don't care about that. This is a special case. And the good things about it is that R is a constant once I apply this.
But it still works because in they apply, as far as I remember, full Herbrandization.
Roughly speaking, yes. So I think I'm out of time, right?
Like 5 more minutes.
Oh, I have 5 more minutes?
Sorry.
Okay, great. So this is the KPT theorem. This is what we're gonna apply. Does it all make sense to the extent possible? Like, why is this sentence better than this sentence? Because I have taken away my existential quantifier over the witness, and I have replaced it with a constant with disjunction, where it's a function symbol, and that function symbol is in p time. And I can sort of hop from disjunct to disjunct by plugging witnesses for these things from my teacher into the thing. Okay.
Where again, just to check, here where it's very important that the student was actually like polynomial time, that's why you're
Yes.
doing this, yeah?
Yes, that is why the LPV function symbols really matter. That's what makes the student polynomial time, is applying KVT to this specific theory. Good, so let's apply KVT to circuit size hierarchy. What do I get I get stuff that looks like this. I get ELF disjunct is a formula, phi with free variables n, z sub 1, z sub 2, all the way up to z sub l plus 1.
Minus.
Yeah, minus 1. And x, and what this says is let h be equal to f sub l of n, z1, z2, zl minus 1, all of the counterexamples that have happened so far. And suppose zi is a circuit of small size. So it's an n to the k size circuit. This is for all I. You'll notice this is somewhat in quotes. Then, oh no, I'm sorry. This should just be ZL. Because I'm saying that I disagree with the last circuit in this list. H on X, so this X is not equal to Z sub L on X, right? So what does this say? This says that whatever you've printed out so far, there still exists an X that is an error, witnessing that this small circuit does not compute the hard function. Cool, okay. So what are we gonna do now? Having done that application, because of the function symbols, again, we can take the following, we can define the following language. We're gonna call it H eval. What does this language take? It takes N, specification of input length. It takes L, a specification of which disjunct it's gonna kind of mirror. It takes counterexample circuits. These are intended to be from the teacher, L of them, to match the disjunct number. And it takes X. And I define it to be just the circuit evaluation of an input bit circuits. F sub L, see this index names which L? Which term to run? And X, okay? So like, what is the claim about this? H eval is in P. Right? Because those function symbols are in P. We can compose together and easily switch on this to get it into P by the, FIs in LPV. Am I out of time now? Okay. Well, what I was gonna do is apply that upper bound on H eval to plug in two small circuits for each disjunct here. Each disjunct was gonna get faults. And at the end, I would have a circuit upper bound of size like N to the 1 plus epsilon to the R. And I can make that smaller than N to the 7K because I can choose my epsilon to be very tiny. And that's the contradiction to soundness of VPV. Major open problem, extract all the hardness. I want better circuit lower bounds than just slightly superlinear from doing this. And it seems like we're missing something, like we can't get like N to the 5 out of this. Thank you very much.
So, yeah, well, quick question about Ido, and
Can you make a stronger theory like S1, 2 or something like this and have it polynomial, not constant in the function?
Yeah, that's what happens when you take S12. And I actually don't understand what goes quote wrong in the proof of KPT when that happens. So that's part of why this is not, but you get more disjuncts, right? So it's,
Because it's not bounded, there is no formula.
yeah. So I don't know anything about S12 provability of circuit size hierarchy theorem implying something weird. I just know about VPV because I need that constant.
All right.
Thank you, Jacob.
Yes, could you say something or maybe a related question? You're somehow using that VPV is not too strong to be able to extract this amazing consequence, right?
Yeah.
So sort of what happens when you know, when you make a stronger or weaker system, like what is it that?
Exactly what Ito said. Basically, this R that we get from witnessing the VPV proof is a constant. If we witness, say, an S12 proof, we get an R that is some slowly growing function. And then I need to do something like n to the 1 plus epsilon of a slowly growing function is less than n to the 7k.
Okay, so
And I can't do that.
at a super naive level, sort of, since the proof system is more powerful, turning a theorem into a witnessing procedure sort of
More
requires.
expensive.
Yeah,
Yes, that's exactly it.
Okay.
When you witness proofs from more powerful systems, you get more expensive witnessing. And we can just barely handle this constant round polynomial student witnessing to get this kind of thing. The beefier witnessing that drops out of S12 and stronger theories don't know how to turn it into a contradiction.
so should we be optimistic or pessimistic? You gave us these two options.
I have no idea. No, I genuinely have no idea. I'd like, in a perfect world, we would be able to find a combinatorial principle that is equivalent to this lower bound in VPV, the way that Igor's talk did, right? Like there's these like special pigeonhole principles that are equivalent to the palindrome lower bounds. If we could find that for this, I would be super happy because then that would say, okay, this is what it can't do. This is why you're confused, or this is what's hard. Here, I really don't know.
Okay, thank you very much. And